In the previous lecture, we were looking at infinite series where the terms were all, for the most part, all the series had positive terms in the series. The sequence of terms we were adding up did not have negative values. When an infinite series, you're summing both positive and negative values, the terms of the sequence are both positive and negative at times, that makes determination of convergence or divergence of the series a little more challenging in many cases. So we want to talk a little bit about those series in this section, and we're going to talk about first absolute and conditional convergence, and then a particular test for determining the convergence of a special type of infinite series where there are negative and positive terms in it. So first we'll talk about absolute and conditional convergence here. So the series, an infinite series, is said to be absolutely convergent if what? We look at that same series and I simply look at the absolute value of the terms in the series. That means if this series has some negative values in it that we're adding up, of course this one will not. Those negative values will become positive. So if there's a negative 1/3 somewhere in this series that we're adding up in the terms, then this will be 1/3 over here. So all the terms in this will be a positive term series. So this is a nice definition, but what does this mean? Well, this next theorem is the game changer, and we'll prove it. And this is real important for this. If a series is absolutely convergent, what's that mean? Again, look at the series, take the absolute value of the terms that we're adding up, see if that converges. If it's absolutely convergent, so if this series is convergent, then the series itself is convergent. And that's a pretty powerful thing. If this series converges, then our original series converges with the positives and the negative values. Okay? So if this series here, the absolute value of the terms in the series converges, then the series itself converges. Okay? And we're going to prove this real briefly, because this is really a powerful thing and a pretty amazing thing. Let's look at this infinite series. And what I'm going to do is a little manipulation, which probably wouldn't seem at all intuitive necessarily until we reach the final argument here. But I'm going to write this as, of course, the a sub n's, and then I'm going to add the absolute value of the a sub n's. Okay, you say, well, you've totally changed the series. But I'm going to immediately subtract the absolute values of the a sub n's. And you might say, well, big deal, right? The net effect is what? That this is essentially adding nothing to it, right? So why do that? Well, just think about, we've used this strategy in a lot of other settings, similar settings, like when we're completing the square. If you remember, we add something and immediately take it away, but then we regroup, and that's what we're going to do here. Provided the following series are convergent, then we can break this up into these two minus just this one. Okay, so I can break up a sum like this, if you remember, provided what? Provided both of these series converge. Well, I know this one converges right off the bat. How do I know this one converges? Well, look at the theorem here. What's it say? What's it saying? If the series is absolutely convergent. So if it is absolutely convergent, right, that means this series what? Converges, right? So we know that is already convergent. The question is this one convergent? Okay, and the answer is yes. And I'm going to prove this essentially by direct comparison. And look at the terms here. The a sub n plus the absolute value of a sub n. Think about what this expression could be equal to. Okay? Again, so the first term would be a sub 1 plus the absolute value of a sub 1. Next term, a sub 2 plus the absolute value of a sub 2, and so on, right? So those are the terms that we're adding up. But think about it. If the a sub n is negative, and we're saying it could be a negative value, let's just make it up. Let's say it's negative 1/3 again. So if this is negative 1/3 right here, what's the absolute value of negative 1/3? Positive 1/3. What's negative 1/3 plus 1/3? It's 0. Okay, and so if this value here is negative, essentially this thing is going to be 0. What if this thing is positive? What if it's positive 1/3? Well, then the absolute value of 1/3 is still 1/3. 1/3 plus 1/3 is 2/3. So I want you to note that, first of all, this expression is always going to be greater than or equal to 0. Right? It's going to be 0 if the a sub n is a negative number. If the a sub n is a positive number, then both of these values are essentially the same. But I'm going to write it a little bit differently. I'm going to say that these values are always going to be less than 2 times the absolute value of a sub n. In fact, if a sub n is positive value, then the absolute value of a sub n is equal to a sub n. And therefore, this whole thing is indeed 2 times the absolute value of a sub n. So it's going to be this if the a sub n is a positive quantity. It's going to be this if the a sub n is a negative quantity. And this is true for every term in the sequence. So essentially, our terms are always non-negative, and the terms in the sequence, the series that we're looking at, the terms that we're adding up, we're comparing it to the terms of another series, if you want to think about it, right? So what about this series here? Do we know whether that converges or not? Well, this too is a constant multiple. I can pull it out, provided this series that's left is convergent. Is this series convergent? Yes, it is. I mean, we just talked about this, right? And so what do we know? This information here tells us that this series here converges by direct comparison. And we talked about comparison tests in the last video. And we can do the direct comparison now because, right, by doing this a sub n and adding it to the absolute value of a sub n, these terms are always going to be non-negative. Okay. So we've shown that this series is convergent and this series is convergent, right? And therefore the original series must be convergent. Okay. Well, I mean, that's the proof. Now, whether or not you believe it or not, it's certainly one that you will want to be able to use. And let me just illustrate this with the next example. So let's look at this series now. N equal 1 to infinity of cosine of n over n squared. Let's list out the terms. When n is 1, I get cosine of 1 over 1 squared, which is 1, plus cosine of 2 over 2 squared, which is 4. We'll just write 2 squared here. Plus cosine of 3 over 3 squared, plus cosine of 4 over 4 squared, plus cosine of 5 over 5 squared, and so on, right? So you get the pattern. Now, what do we know about these terms? The denominators are always positive. The numerators, though, the cosines, so what is the cosine of 1? It's not, I don't know. I mean, I know what the cosine of pi over 3 is, or pi over 6 is, or pi over 2. Well, of course, we're talking about radians here. We know that cosine is positive in the first quadrant, if you remember, in the unit circle. So from 0 to what? Pi over 2. From 0 to pi over 2. Pi over 2 is 3.14 divided by 2 is about 1.57. So cosine of 1 is between 0 and pi over 2. Therefore, the cosine of 1 is a positive number. So I don't know, you can use your calculator and just type in cosine of 1 if you want to. But it's a positive number. Okay. Cosine of 2, however, that's 2 is more than 1.57. It's more than pi over 2. It's in that second quadrant. where cosine is negative. So this term is going to be negative. Now cosine is negative in the second and third quadrants. That's between pi over 2, which is 1.57, and 3 pi over 2. And 3 pi over 2 is going to be equal to a little more than 9 halves, right? So we can just go and say, what is 3 pi divided by 2, right? It's going to be about 4.71. And so between 1.57 and 4.71, cosine is going to be negative. So cosine of 3 and cosine of 4 is negative, right? And then cosine of 5, what's going to happen there? That's more than 3 pi over 2. We're in the fourth quadrant. If you think about it, we're back to being positive. Okay, so the idea is you understand now what's going to happen. We're going to be changing signs, right? Positive and then negative, 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 and then the next, well, I don't know. It might be 3, it might be 2. I don't know. It changes. But the next couple or 3 will be positive, and then the next couple or 3 will be negative, and the 2. It's not quite changing plus or minus every other term. It's kind of sort of a 3 and then maybe 2 and then 3 and then 3 are positive and 3 are negative and then 2 are positive and then 3 are negative and so on. It just bounces back and forth between those. So this is certainly not a positive term series. However, what we just said in the proof above is, let's take a look at this. Right? Which essentially I can just, since the bottom is always equal to 0, I can just say it's the absolute value of cosine of n over n squared. Now we know something, right? All these are going to be now, right, in this series, these will become positive, right? Because I'm taking the absolute value of all these, right? So it's just positive, absolute value. This will be positive, positive, positive. They're all positive, right? Okay, so this series, right, if I can show that this series is convergent, then that means the original series is what we call absolutely convergent. And by that theorem we just proved, if a series is absolutely convergent, then it is convergent. So simply by showing this series here is convergent, we'll show that the original series is convergent. Okay, well, how can I show that this one converges? Well, it's going to be by direct comparison. And the trick is to realize, hey, I know something about the absolute value of cosine of n. I know cosine of n bounces between positives and negatives, but I do know the positive and negative values for cosine. The numerator in each of these is always between what two values? Cosine is always between what? -1 and +1. -1 and +1. So the absolute value, though, is always going to be between what two numbers? 0 and 1, right? And I take the absolute value. So it's going to be non-negative. And now n squared, right, if I divide everything by n squared in this inequality, since n squared is positive, the direction of the inequalities does not change. So 0 divided by n squared is 0. 1 divided by n squared is 1 divided by n squared. So notice the terms of our series, the terms in the series we're adding up right here, right, are less than or equal to 1 over n squared, and they're all non-negative, right? They're no negative values in that. And if I take a look at the terms here and consider this series, do I know anything about this series? Do I know whether that series converges or not? Yeah, we do. This is a convergent P series. All right, remember, P series, P is equal to 2. Anything greater than 1, the series is convergent. And therefore, we can say what? That this series converges by direct comparison. So we're directly comparing it to this P series, this convergent P series. And since all the terms of our series we're adding up are always less than or equal to this, right? And again, the direction of the inequality is important in direct comparison. Then our series also converges. But if this series is convergent, then our original series is absolutely convergent, and therefore by this theorem, it is convergent. So this theorem is real powerful. If I can just sort of essentially, if I'm trying to determine if a series that has some negative values in it is convergent or not, I just take the absolute value and look at that series, which is back to what we've been doing previously, looking at terms with positive terms, a series with positive terms in it. And therefore, this series is absolutely convergent. And I'll say and is hence convergent. From now on, if we say something's absolutely convergent, we won't say and hence convergent. We will just assume it is convergent by this theorem. So if it's absolutely convergent, then it is convergent. Okay. Now, that's a nice thing. Let's take a look at one more example, and then I want to talk about something that is not true about this theorem that may be a little wrinkle. Let's take a look at this series here, and again we're going to be using this stuff because again you can see I'm adding some things are negative, right? Some things are negative. I mean, and I don't know, there may not be a pattern. This looks like plus plus negative, plus plus negative, but I don't know. You know, the pattern may or may not continue that way. Might just be random negatives. But again, if I look at the absolute value of the terms, let's call these terms a sub n, then of course I just get 1 plus 1/3 plus 1/9, right? That negative 1/9 becomes positive, and so on. So let's look at that one, right? Well, what kind of series is this? Do you recognize what type of series this is? Okay, it's one of the first ones we looked at, right? It's geometric. The second term is what? 1/3 times the first term. Third term is what? 1/3 times the second. 1/3 times 1/9, 1/27. 1/3 times 1/27, 1/81. So I'm multiplying. This is geometric series with the ratio r equal to 1/3. And so since the absolute value of r, which is 1/3, is less than 1, we know what? This series converges. Right? And therefore, the original series is convergent. Absolutely convergent. And hence convergent. Okay, so we'll just call this a sub n, so that's what we're talking about. So that series is absolutely convergent again by this theorem. Okay, so pretty powerful again. So if you got some negatives in there, we can deal with that. Now, there is a problem with terms that have positive and negatives in them, and let me show you a situation here, and we'll come back to this theorem. So let's take a look at this one here. Pretty simple looking thing here. Let's list some terms here. What do we got? When n is 1, what's going on? I got 1 down here. What's going on up here? 1 minus 1 is 0. Negative 1 to the 0 power is 1. So 1 divided by 1, I get 1 when n is 1. When n is 2, the denominator is 2. But here I get negative 1. 2 minus 1 is 1. Negative 1 to the first power is negative 1. So this will be a negative 1/2. Okay. And then when n is 3, I get 3 minus 1 is 2. Negative 1 squared is positive. I get 1/3. Okay, I think we see the pattern now, right? Next one will be what? Negative what? 1/4. Then what? Positive 1/5. Then what? Negative 1/6. And so on, right? We get this sequence now, our series series we're adding up an infinite number of terms, and now like the past two, we have some negatives and some positives, but there's certainly a pattern here, right? You know, positive then negative, positive then negative, positive then negative, positive then negative. So there's certainly a pattern there. Okay, well let's do our trick then, right? Which is what? Let's look at the absolute value of this. And essentially when I do that, what's the net effect? this thing up here, this negative 1 to the n minus 1, is either what, positive or negative 1. It's sometimes what I call a sign changer, right? Once I take the absolute value of that, though, it's always 1, right? No matter if it's, negative 1 or positive 1, it's always 1, so it's always 1 over n. This is the one we're looking at, right, of course, which is 1 plus 1/2 plus 1/3 plus 1/4, obviously, and so on. But does that series look familiar? I hope so. What do we know about this series? Is it convergent or divergent? I'm talking about this quite a bit, right? It is divergent, right? It's the harmonic series. Or remember, it's a p series with p equal to 1. Remember, if p is less than or equal to 1, then the p series is divergent. If p is less than or equal to 1. This is kind of a borderline p series between the convergent cases and the divergent ones. All right, what does this mean? Well, this series is not, right? This series here, so the series that we started with here, negative 1 to the n minus 1 over n, is not absolutely convergent. Okay, now, so does that mean, therefore, can we conclude, hey, if it's not absolutely convergent, then the series does not converge? No. Go back to this theorem, right? All the theorem says is that if it is absolutely convergent, then it's convergent. It doesn't say if it's not absolutely convergent, then the series is not convergent. And so we've got some of the nastiest series now to talk about, and those are ones that are not absolutely convergent. Now, what could be true about this series then? We don't know. It could be divergent, but it can also be convergent. And such series that are not absolutely convergent, but they are themselves convergent, are given the term conditionally convergent. So a series is conditionally convergent, or converges conditionally, if the series converges, but the absolute value terms series diverges. In other words, it is not absolutely convergent, right? This means absolute convergent if this series converges. So if it's not absolutely convergent, but yet it still converges, then it's called conditionally convergent. And finding out whether a series is conditionally convergent can be quite the task. But for the one we just did, or any one where we have an alternating sign pattern, we can get an alternating sign pattern like this, then we have a nice little theorem that we're going to take a look at right now, and then we'll come back to this one and see if we can determine whether or not it's convergent. So if we have what's called an alternating series, then we have this nice little test, and I want to talk a little bit about it, sort of how it's working. But these are series that look like this, and you might say, hey, this looks familiar from the last one, right? This negative 1 to the n minus 1 might be negative 1 to the n, or even negative 1 to the n plus 1. It's just going to be what I call the sign changer. This is the sign changer. There's other ways to denote a sign changer, but this is the common way of doing that. And basically it just alternates the sign between positive and negative for every term. Notice when n equals 1 here, this will be negative 1 to the 0 power will be positive 1. So, it's just, the a sub n. And the a sub n's, and by the way, are greater than 0 in this. So these a sub n's are kind of like if I took the absolute value, I would just get a sub n's. Right? These are always going to be non-negative. In fact, we got them actually being positive, but so that means this sign changer starts off with being positive term, and then the next one will be negative and then positive. This one, notice when n equals 1, you get negative 1, so it's going to be negative and then positive and negative positive. So it just depends on whether you start with a positive or negative term. Okay, so these types of series, these alternating series, they are going to be convergent. They'll converge, and this is real important. This test only tells us about convergence. It will not tell us about divergence. So the two converge if what? The terms that we're adding up go to 0. Now, it's important to realize for any series that is convergent, this must be true. But just because this is true doesn't mean that the series converges. Case in point, the harmonic series that we just looked at. The harmonic series, right? Remember the harmonic series when we were just looking at this, right? Clearly 1 over n, the terms, goes to 0, right? The sequence, the numbers that we're adding up, they're going to 0. The limit is 0. But the series adding up all those terms is infinite. So therefore the series is divergent. But with